Hello and welcome. In this video, I want to take a look at parametric surfaces. Now, back in Calc 3, we had the notion of vector-valued function, right? That is, you had one input, usually it was t, and you had multiple outputs, maybe x and y if you're doing this in the plane, or x, y, and z if you're doing it in space, right? We called them vector-valued functions. One variable in, two or three variables out. Of course, you could do more variables if you're in higher dimensions. And we thought of these as parametrized curves. That is, for each value of t, you calculate an x, y, and z coordinate and plot that point. And then for the next value of t, you get an x, y, and z coordinate, and you plot that point. Now, you think of it either as a vector from the origin pointing to the point, or you think of it just as the point. If you think of it just as the point, you're describing a curve. And actually, I think of it as you're describing motion along the curve, where t is like time. And so you can not only describe a fixed set of points, but you can do it as a path. You can say, hey, I'm traveling along this. I'm doing it this way, or I'm doing it that way, or I'm going really fast over it, or I'm going slow. Or, I mean, you can do all sorts of things with these parametric curves, right? Vector functions. Now, I want to up the number of inputs. So rather than having one input and multiple outputs, I'm going to have two inputs and multiple outputs. So I have r of u and v is x of uv, comma y of uv, comma z of u and v. Now, in a sense, we've dealt with things like this already. Vector fields have two variables in and two variables out, or three variables in and three variables out. But I want not the same number of inputs and outputs. I mean, these can have two variables out, but they visualize them better if there's three variables out. So precisely two variables in and any number of variables out, and we're calling this a parametric surface. Okay. Most of the examples will be three variables out, so that will be in R3. Now, because we have two variables of input, I essentially think of that as 2 degrees of freedom. One variable of input can describe a curve. Another variable can describe a curve maybe in a different direction. So the combination is you've got different families of curves where you're varying one of the variables, or the other family where you're varying the other variables. And I actually see these as grid lines on the surface. So for instance, here's a cylinder. This is r of u and v equals, first component is u, the second component is cosine v, the third component is sine v. Now, just look at the y and z components there, cos v, sine v. That if you didn't have that first coordinate, this would just look like a parametric curve. In fact, it would look like a circle in the yz plane. Right? But there is another variable because the x coordinate is being used as u. So for each different value of u, you can vary the value of v and you draw one of these circles. That is, these, in this picture, these vertical things, which would be circles going around, are constant values of u where v is allowed to vary. Also in the grid here, I see these horizontal lines. That is, for each value of v, you've chosen a point on the circle, one point, and then u is allowed to vary. That is, the x-coordinate varies. So the horizontal lines here are all constant values of v. So that grid you're seeing are constant values of u and constant values of v. I find this important because I see two skills here. The first skill is being able to look at a set of parametric equations like this, or a vector function of two variables, and say, oh yeah, that's going to be a surface, and get maybe some idea of what that surface is going to look like. The other skill, which I think is even more valuable, is to be able to look at a surface and say, can I parametrize it? Can I come up with this vector valued function of two variables? And the way generally I do it is I visualize what grid system I want. Can I picture certain curves? Can I picture a family of curves going one way? Can I picture a family of curves going the other way? and then describe those curves in terms of the two variables. Anyway, this one right here, we can look at it in 3D, and it pulls it up in CalcPlot 3D when I click on it. Oh, if you're actually in my class watching this video and you have access to the wall map page in Will's notes for this week, you have this whole document with the active links. Yeah. So that is looking straight down the x-axis here. You can see in the YZ plane there are these circles. All right, so that's a cylinder. Let's look at another example here. Yes, this one. U cos V, U sine V, V over pi. Now again, if you think in terms of, let's see, just x and y this time, I see polar coordinates there. I see like an r cos theta and an r sine theta, where u is playing the role of r and v is playing the role of theta. So this somehow is going to have circles involved. That is, if you let u be a constant, then cos v sine v is going to give you a circle of radius u. Okay. Now, it's not actually a circle here because while you're drawing that circle, v is also being used to change the z coordinate. So as you're trying to draw a circle on the x and y plane, z is getting bigger. And so you're drawing, I almost said spiral, it's not a spiral, it's a helix, right? And so there's grid lines that run this way, down around this surface. Those are constant values of u. On the other hand, if you look at constant values of v, and you let u vary, well, if you have a constant value of v, the z coordinate is just staying the same. If you pick a constant value of v, then on that circle, you've chosen a particular point on that circle. All that's changing now is the radius. U is being allowed to change. So you've got a constant value of z, you've got a constant angle essentially, and you're just moving along that line. And so these horizontal lines here are all constant values of v, and hence constant values of z. And you get those, I guess I can't rotate it here. Let's click on it and bring it up in CalcPlot 3D. And you can see this surface. This is called a helicoid. Screw, essentially. If I look straight down the z-axis, it's always tricky to get it right exactly straight down the z-axis, but that's pretty close. You can start to see those circles, right? That is, if you couldn't tell that the z was changing, you're looking straight down on it, you can see these circles for different values of u. But they aren't actually circles because the z is changing. Those circles have been turned into helixes or helices. What's the plural of helix? Yeah, and then of course these horizontal lines here are constant values of v. All right, what's the next thing we want to do? Next example. Oh, the next example is, let's do it the other way. Let's find the parametric equations for a cone. All right, so what I want to do here is I want to pick the cone. That was supposed to go through the origin there. I'm thinking of the cone, let's say with the z-axis down the middle of it. And let's just do it so that essentially it has slope 1. For every time that you change the radius by 1, the z will go up 1. Okay. So I'm picturing now a grid on this. I'm picturing one set of families which are circles going around like this. And I have another set of curves that are these radial lines. Radial lines. I mean, they're going up and down the cone. They're not changing at all. So one set of curves looks like circles, right? But the circles are changing in radius. So and it's in the XY plane. If I look straight down the Z, I'm going to see those circles. So it looks like I'm going to have a U cos V and a U sine V again, like I did last time. Okay. But as I look at each one of those circles, the Z coordinate is all the same. So the Z coordinate can't be changing as I move. The thing that draws me around the circle is changing the angle V here. So I want the Z coordinate to be dependent on U. So this was U cos V, U sine V. I think if I just make it equal to U, then that should do it for me. R of U and V. Yeah. Notice if I pick a constant value of V, then I've chosen just a point along the circle somewhere, and then I allow U to change. That's just changing the radius of the circle, but at the same time it's changing Z. And the radius of the circle and the Z value are the same. They're both U. And so you'd be going up and down this line. I'm allowing U to be positive or negative. That would make Z be positive or negative. And you get that line. If you chose a different value of V, then you'd be doing, a different line up and down that cone. Let's hop back over to here. No, let's go to here. So, yeah. So we had that helicoid. The difference here is, let me get my face out of the way. The only difference was we changed this to a U. Yep, and sure enough, there's our cone. So constant values of V are giving us these circles, but constant values of U, no, other way around. Constant values of U are giving us those circles. Constant values of V are giving us these lines along the cone. And you can change the pitch by changing the relationship between U and Z. If you wanted to go up faster, make this a 2U, right? So it grows more quickly. Or if you want it to be less quickly, make it U, divided by 5 or something like that, so that it doesn't go up as fast. Right? So you can do all kinds of things to make different cones. You can also, vary the X radius versus the Y radius. So this will have the X's twice as big as the Y's. And let's go back to just divided by 1 there. Right? So in this case, you're getting elliptical cross sections because the X's are stretched by a factor of 2 where the Y's aren't. Right? This is an elliptical cone. So you can do all kinds of things. It's interesting with CalcPlot 3D here. I'm going to turn this thing off for the moment. And if I go up here to select and say, just give me a parametric surface, it randomly gives you one, right? And sometimes it's a sphere, sometimes it's one thing or another. This time it happened to be, oh my goodness, it happened to be a Mobius strip. I'm going to have to come back to this Mobius strip example in another video when we talk about orientable surfaces, because this one is not orientable. But yeah, it's like, let's try another. Give me another parametric surface. And turn this one off and turn this new one on. What did I get? I got like a big old trumpet flare here. Yeah. All right, turn that one off. Try one more. I find it just a good way to see some examples. Like other things that we've done. I don't want to show you this one because that's my next example. Like other things that we've done, you haven't done this before, and so taking some time to play with it, to experiment, see what kind of See what kind of surfaces you can create. See if you have a surface that you want. Can you create it? And the thing is, I do have a surface that I want right now. I want a torus, a donut, a bagel, whatever you want to call it. Something like this. Okay. Now, I'm going to come up with a parameterization for it in the following way. That is, I need to think of a grid. That's the way I do it. I think of a grid, I think of one family of curves, and I think of another family of curves that kind of cross over it, cover up the whole surface. Right? So one set of curves are going to be the circles that go around this way. And the other set of curves will be the circles that go around this way. And I got a pretty good idea of how to do circles. But here's the way I'm going to do this. So let's look at this and say, there's going to be, how am I going to do this? My two parameters are going to be essentially an angle from, let's call the x-axis, the y-axis, the z-axis. So in the xy plane, let's draw an angle, let's call that u. And then if I extended this way, keep it going a little further, but I'm going to go up to here, and this is up towards the z direction. This will be an angle I'll call v. Okay? And so this point right here, I've got to be able to describe the x, y, and z components in terms of those two variables. So as I think you can see here that keeping v constant and letting u vary is going to create one of these kinds of circles. But keeping u constant and letting v vary is going to create one of these kinds of circles. So, first of all, I think I can clearly see the z coordinate, because if I drop a perpendicular down here, then I've got this this angle v. If I knew how long that hypotenuse was, then I would know the z coordinate right there. Okay. Now, I have to make some choices. So let's say that this is length 2 out to here, and this is length 1. Okay. So the z coordinate here, the z, is going to equal just 1 times the sine of v. Likewise, this side down here is going to be 1 times the cosine of v, because that would be the adjacent side to that angle, and the hypotenuse is 1. So this down here is just cosine v. And I need that because to get the x and y coordinates here, I need to get the x and y coordinates right underneath. So this would be the x coordinate, that would be the y coordinate, or maybe it's, I said this, but the x coordinate here. So this length is the x coordinate, this length is the y coordinate. And the x is the hypotenuse times the cosine of u. Well, the hypotenuse is 2 plus cosine v, and then I need to multiply by cosine u. The y coordinate here is the hypotenuse times the sine of u. And again, the hypotenuse is 2 plus cosine v, and then multiply by the sine of u. So this should be the parametric or a parametric representation for that torus. And if we jump back over to here, move my face out of the way, and you look at the formulas they give here, x is 2 plus cos v cos u. So I think they have their, no, this is the same thing. This is what we did, right? And if I hit that, say enter, then sure enough, it looks like it's sideways, but the z-axis is pointed the wrong way. There's my torus. And I can see how to change things here too. If I want it to be, say, bigger, main diameter, I can change this 2 to a 3, for instance, and the whole donut should get bigger. Yeah, right. Or if I wanted, a skinnier tire, think of a tire, that is, the radius here is in the other direction is smaller, then instead of like sine V, I might say sine V divided by 2. If that's all I do, it only makes it skinnier in the Z direction, but it didn't make it skinnier in the X and Y direction. So let's divide that by 2 and divide that by 2. Oh, that wasn't the right thing to do, was it? That whole thing got smaller because I didn't want to divide the whole x coordinate by 2. I only wanted to divide the inner radius, the radius of the other circle. So this was the sine v divided by 2. I need to divide the cosine v's by 2 to keep that radius bigger. And as I took that radius of 3 and essentially made it a radius of 1.5 with my divided by 2. But this way, let's try this. There we go. That's still got the radius of 3 to the center of that torus, and then I only have a radius of 1/2 for the other direction of the circle. And notice the grid on it, right? The grid are constant values of v or constant values of u. There are some really cool things that you can do with donuts, with torus here. For instance, I'm going to switch from v's in here to say u plus v. And enter. And what just happened there? The grid just started to sort of spiral around this thing, or helix around this thing, or anyway, it's not one direction is still going straight through, but the other direction is going in and out and looping around. And in fact, if I do here, instead of u's, let's do u minus v. What just happened? One of the things that just happened is I'm drawing this thing multiple times over because now it's going around too many times. Oh. Maybe oh, I see what's happening. One says 20 and one says 40. Let's make them both 40. No, that still didn't get me there. There we go. Just fabulous. Just fabulous. So, my advice to you, my encouragement to you is play. See what sort of surfaces you can come up with. Just play with the formulas and see what happens. And see if you can actually get specific surfaces parametrized. Okay? Just build your vocabulary on parametric surfaces. It is so much fun to be able to just create these things by just giving it an equation. And you get some beautiful, beautiful surfaces. Anyway, enjoy.